Yeah, pleased to be here. Before I do my introduction, so I'm going to talk to you about the meta and how they made MySQL work at scale. Previous speaker, Vittorio, did fail my opening question of how many of you knew that Facebook used MySQL, but anyway, let's skip that. In the reality, the topic should probably look something like this, with like lots of remarks, and we're going to see why. Particularly, for example, meta is huge. We're going to talk specifically about Facebook and what is called UDB, the user database. And there's lots of remarks that I'm going to make throughout the presentation. So as usually with big tech, there's lots of nuances. Cool. Yeah, so at the moment I'm engineering director in a company called Go Cardless, based here in Riga. But I had spent some time in Facebook in solutions engineering and worked with MySQL as a developer for almost 10 years. I've seen SQL without views and triggers from like SQL 4 and stuff like that. So yeah, it was long ago. It probably feels like I'm on the right on this photo, a small boy. But yeah, also one remark here is my perspective will be from sort of an engineer not on the database team. So I'll give you some of the kind of knowledge and the perspective of how it looked for engineering, but there's lots of nuances under the hood that sort of only database team knows and manages. All right, so we'll actually start with a little bit of the exercise of, say you're, I don't know, in the interview, and in 5–10 minutes, you need to design something like this. Not even the whole feed, but a simple page where you can see a post with, order, some information, media, and like comments and likes, right? So most likely, you're gonna end up with like roughly something like this. Maybe you'll put some like load balancer in front. You'll have kind of application servers and different nodes. Probably you put some cache in, and then you have database. Maybe one. Maybe you'll decide to use like read-write replicas and stuff like that. So like, or do some sharding. And in terms of data model and design, like the sort of simplest 10-minute solution version could look like this, with users, post, comments, likes, and kind of relations between them. But we have a new incoming requirement, so how to actually make it work at scale. And we mean it has to be a worldwide service now. It has to deal with about 10 billion object queries per second. It's object queries, not a network request, so quite a lot. We are dealing with multiple petabytes of data. Our read-to-write ratio is quite skewed towards the reads. So you can see that only a fraction of the percent actually goes to writes. We also have to deal with kind of a power law distribution of the popularity. So some of your popular users or popular posts will get a lot more attention than the long tail of the less popular stuff. You have to guarantee low latency and eventual consistency, so it means not immediate consistency, but over time, kind of after writes or modifications, the information should propagate and be consistent. And we're dealing with the complex data access control model. Also, important condition is that you cannot just say, screw my current database and come up with some new solution, so you have to evolve rather than start from scratch. So you don't have an opportunity to design it from the ground up. Right, so let's actually deep dive into some of the principles that allow Meta to scale and use MySQL for their Facebook product. And the first thing, like a quick introduction, that most of the data is represented as a graph. Like people, posts, comments, likes, etc. And the graph is, basically like a set of nodes and the links between them. It can be directed, undirected, and we're gonna have some quick exercise of like deciding whether something is object or association. Hopefully quite simple, but just to kind of warm you up. So what do you think about the person? The obvious one. Object or association?
Object.
Okay, good. What about a like? Yeah, right. And it's also directed in one way. So usually if I'm liking the post cannot like me back. What about the friendship? Yeah, one way or like directed, undirected?
Two-way.
Undirected, yeah. So if we are friends, it cannot be on the Facebook, it cannot be that I'm a friend of you and you're not a friend of mine. So what about post? Follow? Directed or undirected?
Directed.
Yeah, this one, unlike the friendship, I can follow you, you don't follow me back. So that's possible. What about the click on the advert?
Association.
Yeah, so that's association and one way. So user clicks on ad, not the other way around.
But there's an event of ad click consisting of everything, like your operating system and all of your tracking.
Oh
data.
yeah, that's the association that has a lot of attributes attached to it. What about if your username is tagged in the post? Yeah. We're almost there. Comment?
Object.
Yeah. What about a reply to comment?
Object with association.
So that's tricky. The comment is object, but the relation that this comment is a reply to another comment is an association. Cool. So a quick warm up. And yeah, like, you know, why don't we, if everything is a graph, like why don't we just use a graph database? I guess here, like, first of all, at that stage, when Facebook was scaling, even the concept of graph databases was relatively new. Second, again, you're at your scale, you're dealing with a situation where none of the out-of-the-box solutions gonna work for you easily. And third is it violates the principle of evolution. So you cannot just start from scratch. You know, they started with MySQL, so it's not really gonna work. Okay, so let's look at the first principle, denormalization. So that's where we are at the moment with our data model. And yeah, I love this meme, and I think we're gonna illustrate it with one fun example of how you know, what works at that like medium level is not gonna work at the far end. So there's this thing called Bieber problem. I don't know if anyone heard about it. Yeah, so basically the story goes, it manifested in actually two different services in two stories. So there's one story about the Twitter, not X back in the day, where they were, the way they built the feed was basically stretching them very thin when you deal with a very popular users. Because if a million people follow somebody, they were like pre-built in the feed, and it was like absolutely like smashing the database when they tried to inject it into every, like during the feed generation to use that relationship for building the feeds, because so many people follow the same person. And it's like, the story goes that it happened to, like, based on the Bieber account and like his followership. The same was true about Instagram, not Facebook though, where they realized that the aggregate functions slow down because of the things like this, where if you need to count likes on, yeah, like in our case on the post likes table, like you run this, and because of the aggregate function, you start hammering database, and you have lots of read requests, and it all happens, all results in this query. So yeah, I mean, instead, let's do it faster. So we can, you know, introduce some denormalization, put a counter on the table, and now it's a very simple select one field operation. Although, again, the remark is that, of course, you need to update the counter every time the like event happens. Yeah, so where we kind of can get to this with this is based on your application requirements. You may decide to denormalize some stuff, and like in our example, like you can have, you know, maybe post counts or most recent post ID or most recent post time for a user, so that you can somewhere say like you posted, you know, 2 days ago, and you can like, yeah, pre-calculate the likes count, comments count, and stuff like that on the post level. So it's very application dependent, and once you realize that some queries are slowing down, you consider the principle of denormalization to speed it up. Yeah, so with that, we're gonna, every time we introduce a principle, we're gonna look through the requirements and check like where we had some hopefully positive impact. So with that, we sort of addressed the Pareto distribution, where it's this approach would be optimized for celebrities because it optimizes the queries, and then again it optimizes for reads rather than writes. So we complicated the write a little bit when the like happens, but we simplified the read. But we sort of, with denormalization, I think we made the situation with the volume of data even worse, because you start introducing those columns on the tables, and the tables grow, and yeah, so not a great progress here. We're gonna make it actually worse before it gets better with the indexing, which is a second principle. So, like, you know, what do you do in this case? Well, index everything, right? And that's sort of what engineers did. And that, of course, resulted in a growth of the data as well, because you need to store indexes. So the, I guess, like, yeah, it mentions like in the DB engine, I guess I don't need to introduce the concept of like engines in MySQL. Everyone understands what is that. Okay, I'll skim through the next slide then. So the problem Facebook had at the time is that on their database nodes, the most sparse resource was actually space. So they were only utilizing about 20% CPU on average, 50% I/O, and with that the disk was the bottleneck. So yeah, that's a poor analogy. So yeah, the solution is always, like in all those remarks, is always a file or a chisel or like whatever you call it. But basically, for by that time, Facebook was already using RocksDB in some other applications, and like, why not trying to make it work for the Facebook application? The problem is, like, RocksDB at the time lacked some of the functionality they relied on. For example, they built a very robust replication mechanisms in MySQL. RocksDB didn't have that, and also RocksDB didn't have a SQL interface itself. So it's more of a like a key value storage. Basically, the idea was that let's, instead of, we cannot use RocksDB, but let's create a MyRocks engine and replace InnoDB to get the gains from the RocksDB. So the jumping into sort of the results, the outcomes, they've made actually like a positive impact on CPU as well. So it lowered by 2%, the I/O lowered by 3%. But the space, more importantly, like pretty much halved. So it allowed them to more efficiently use every database server, because you can store twice more information. The sort of why it worked is not a, like more of a the deeper computer science topic, but basically RocksDB and MyRocks, they use a different storage structure called the log structured merge tree, which is A, more space efficient, and B, it optimizes for faster writes, basically. I'll show on the next slide like why. Yeah, it's, as I mentioned, a key value storage. It has some additional features like Bloom filters for kind of the faster lookups. It has an ability to set the certain configuration based on the column families rather than the whole table, so you can like optimize like how you can have a multi-column index the same way you can optimize, fine-tune your tables based on the column sets. There's also like some nuances about the InnoDB using sort of a fixed page size and the RocksDB using dynamic page size, and a lot of like compression that happens. But very simply, in the LSM, what happens is you write sequentially rather than trying to find where to write. Even if it's like a B tree in InnoDB, it still takes time to figure out. Here you write sequentially, and then there's a couple levels of what is called compaction, where you aggregate files and you sort them, and you aggregate again and sort again. So usually there's like 2 or 3 levels of the compaction, and that allows the faster writes and more efficient storage, because in InnoDB there's like lots of gaps left in the pages, also because of the fixed page size. Right, so that's a big win. So how actually, there was also a state of art how the migration happened. So usually on the same database server, you usually have like the SQL interface and the replication is what you have from the MySQL engine that was not possible to replicate with RocksDB. And then within the server, you can have sort of an InnoDB tables and MyRocksDB tables. So they were slowly migrating tables from one type to another. And in terms of the servers, usually it happened through like introducing the MyRocks slave first, then maybe adding another one, and then promoting like one of them when they ran all the, like there's a confidence in the data matching and the mirroring, you could promote one of your slaves to become a master. Yeah, so that's one of those like remarks that I mentioned, where it's like, yeah, it's MySQL, but you know, really under the hood, there's already like some shenanigans. You see there's different engine types, and you know, the key things, I'm sure there's more, but the key things is they needed the replication and all the tooling built around MySQL and the SQL interface itself as well. So let's do another requirements check. So we definitely optimized writes for lower latency. We follow the evolution over revolution principle, and we have a lot more space-efficient storage now. I mean, we still need to deal with the number of queries, so maybe let's look into that next. And the next principle is caching. Again, another sort of reality. It's all started with memcached. So at the time, there was a choice made, and it's very fast, but it had no replication, no sharding, no persistent, and also a bit of an app-specific concept that there was a lot of like all-to-all due to the high fan-out of the request. So basically, if you're looking at building even that simple page, but more applies even when you need to build a feed. One request of give me my feed results in like hundreds of objects requested, like all the posts and their orders and comments and all that stuff. So there's a huge fan out, and those objects of course will be distributed through different cache servers. So you have to speak to a lot of them before you can serve the response. Yeah, so we're gonna jump like straight into what Facebook came up with. So it's sort of like a three-layer system where they've introduced on the application servers themselves. They've introduced like a utility called the macrouter that knows how to like find the right shard by the object ID. There was also introduced a level of the local cache. And then two tiers. Two-tier system with the follower and leader tier, and it's sort of similar to the read and write replicas for database, where the write requests go to the leader tier and the read requests go to the follower tier. So that minimizes the load on the write operations. And yeah, basically the request follows this path. Like, let's check the local cache. If no, let's go to, if it's a yeah, the read request goes to the follower tier cache server. If there is a miss, it goes to the lead tier cache server and only then queries the database. On the writes, it's that, so it goes straight into the lead tier cache server, goes to database, and then as a result, we issue either invalidation or refill messages to the follower tiers. And the difference is, you know how we looked at the object and association? So basically for objects, they usually do invalidation, and for associations there is an async refill. So there is a sync process that will invalidate and refill the association with the new updated information. So that's how it works on writes, roughly. So yeah, in terms of the details, basically like 99% of the requests end up in either L1 or L2 cache. It's write through, so you have the read after write consistency. If you query the same node, because if there's invalidation, there will be a cache miss and it will propagate the updated information. The caching is consistent. There's also like interesting concept that your client-side sessions are somewhat sticky to the application server. So if you're using like Facebook app, it will attach you for sometimes like multiple days to the same application server. So your L1 cache is utilized quite a lot. There are also some, like if you're into networking, there are some tricks that they did with configuration of the memcache, where it uses the UDP connections for GET requests and the TCP for writes. So for writes you need more guaranteed transport. For reads they could afford a fraction of percent drop rate on those requests. They introduced batching, so with that fan out I mentioned, you're still gonna end up with out of the 100 objects you need to get, you're gonna end up with some number of objects that are gonna sit on the same cache server. So what they do is batch those and get multiple keys and objects in one request. Lots of compression to minimize latency, and also quite complicated mechanism against the stale sets and thundering herds. I don't know if you heard those concepts, but like stale sets is when your writes come in the, say, reverse order, and you get the this conflict of the wrong information written on top of the right one. And the thundering herds is basically what they call a extremely hot objects that get a lot of reads and writes. And so there's a special special mechanism to deal with those situations. And also quite complicated infrastructure to manage kind of the distribution of keys, the load, replication, and the whole like sharding. If something goes down, how to kind of like replace it, all of that stuff. Yeah. So in terms of the requirements check, let's have a look. So we've dealt with we have a distributed cache, so it's now like better in terms of data. Again, it optimizes for the read heavy load that we have. We have a high cache hit rate, so it lowers down the latency. We don't need to query database, and the type of the mechanism for the cache, which is write through, kind of gives us eventual consistency and read after write consistency as well. Right, let's look into the next concept, which is replication and sharding. So this is to remind where we are, and so we still kind of like having that database server, or like maybe read and write replica that we saw in the original diagram. Right, so the things with replication, like starting from simpler, like you have master and slave, you can have multiple slave servers per master, and you can distribute them across data centers and regions. We're gonna introduce the concept of regions. I'm gonna show how it all works across the data centers in the regions. And also, in terms of the replication, it's the format they use is binary, and they used to have a statement-based. Now it's, I think, mostly row-based replication. The fun fact is, for statement-based replication, they managed to put some kind of system messages used between the follower and the leader cache tier through the database. So it was like part of the bin log. So lots of hacks.
Max, can I ask a quick question?
Mm-hmm.
Can they scale like that endlessly, basically, of this combination of MySQL and routes? Because like MySQL, I believe, has some bottlenecks of how far they can go. In case of Facebook, how it goes?
I mean, it took them to like what 2 billion users. So if not endlessly, then at least on the scale of the globe, yes.
So it's basically more servers, and that's it. And schema works.
Yeah. The schema is actually, so I'll talk quickly about sharding and we'll see the schema. Yeah, so sharding based on the object IDs. The sharding for database is different to, just to be clear, different to the caching sharding. So it's not the same algorithm. And for like the time-based tables, they pre-create buckets for the future periods. And then you have a mechanism to deal with like hot shards and hot objects as well. Basically, for the replication and sharding, let's look at actually one of the trickiest scenarios where it's the write request and we have a cache miss, and besides that we're dealing with a follower tier, so where there is a slave database rather than master database. So when the request comes in, again the same mechanics, we check the local cache, we go to the follower tier cache server. What happens next is, because it's a write request and we have only slave in this data center, we need to go across data centers to another leader tier cache server, which will then find the master DB shard and write there. And from there we have the sort of dotted dashed lines, which is the async replication to the slave DB shards, and then also the message, the invalidation messages still propagate to from leader tier to follower tier and to application as well to invalidate the object. So overall it looks like this, like pretty unreadable and complicated. But yeah, let's check. So we have now expanded this to a worldwide scale. With sharding and the cross data center and cross region replication, we can deal with volumes of data more efficiently. We sort of dealt with the low latency and the eventual consistency as well, because through the async replication and the propagation of messages between the cache tiers. Right, the last principle is abstraction. So the interesting aspect that with all of that, we still, you can see in that like application block, it's still quite a lot of like logic of all of this, like traveling and knowing where everything sits. So your application have to speak to different layers of the caching servers. It has to deal with very complicated data access rules. You have potentially like some application level joins. You need to understand the structure and like deal with database connections and all of that. And on top of that, you have all the like observability and monitoring of the the queries and the performance and all that stuff. Yeah, not really easy to, if you're a product engineer, not really easy to deal with all of that. So the answer to that is something called the TAO, presumably standing for the associations and objects. Yeah, the concept is basically that everything can be represented in the form of like object has an ID, a type, and some key value list of properties. An association consists of two IDs, association type, some timestamp for the creation, and again the key value list of properties. And you have a programming interface for engineers where you can sort of like read operations and the standard CRUD write operations as well. Basically, our schema for the post that I showed in the beginning could look like this. So you have, this is the person object with these properties, it's another object for the person, and then the ordered means like I posted a post. This is the reverse association, so the post knows who is the author, and you represent the likes and comments in a similar way. So let's look at the sort of like how the pseudocode for this could look like. You don't need to deal with all of these like cache and connections. So you can request the object. You can deal with you know, getting associations. This, for example, is for post, and there's two examples. One is where you don't use denormalization, and for example, you fetch the order of the like separately. And for the comment, I showed that maybe you use denormalization, and the comment author you fetch from the comment object rather than go separately to the order object. So yeah, in the reality, you want more optimizations like this rather than like this, but this is how the pseudocode could look like. Right, so what does the Tao do? It abstracts the data access, kind of similar to the GraphQL concept, where you don't need to know the underlying database structure much. It abstracts all these like caching complexity, the follower, leader tier, all of that. It does all the monitoring, observability, like slow queries, all that happens under the hood. It handles consistency isolation, and everyone can specialize like what they do the best. So product engineering can work, understand their product domain and build the product, and the database team can deal with you know, tuning the database tools and the Tao layer at that stage. It's also important to understand that the Tao interface is not the same that actual like underlying table structure, but it's a very useful abstraction for engineers. So checking the requirements again, like we abstract all the complexity. The Tao helps with serving the load, getting consistency, and also more importantly the data access control model as well. So all the rules, like, you know, can this user see a post of this user, and there's multiple rules whether they, I don't know, blocked or marked as, you know, like don't show me posts from this user. Like all that underlying complexity can be handled by Tao as well. Right, so stitching it all together. It's actually also important to know that, you know, those arrows between the cache servers, it's not how it works in the reality. It's not the cache servers speaking to each other. It's like some layer, whether it's application or in this case Tao, that deals with that. And you can see that basically from the complexity left, we still have the L1 cache that application have a notion about. But otherwise, there is a special protocol, the RPC protocol, to talk to Tao servers, and then the Tao servers deal with the routing, they deal with kind of sharding, they deal with all the cache servers, and then you have the replication and the cross data center messaging to like propagate information between data centers and regions. And by the way, for all of that, there's like custom solutions developed in Facebook for almost every aspect. So you have a separate bin log server, you have a separate replication tool that kind of does this thing instead of the standard ones. And then in terms of the data model layer, you can still have these like generic object tables if you don't need much of the optimization, so you can literally mimic the Tao structure in the database. But more often you have the more specialized tables where you do have the kind of like hot columns outside of the blob existing on the table level, and denormalization that we mentioned, like all those things. Right, so the other aspects that we haven't mentioned but worth mentioning is that at this stage, they, apart from the MySQL plus MyRocks, there's lots of developments around ZPDB, which is used more and more. There's lots of processes in the background, like one fun example with the associations that have the main association and reverse association. They guarantee the right of the main one, that is like part of the transaction. If it doesn't happen, then the request fails. But the reverse one is not part of the transaction, so if it fails, then there is a separate background process that will pick it up, find the hanging link, and create the reverse association. So there's lots of nuances like this. There's insane level of instrumentation for engineers, insane level of like logging and observability and keeping track of everything in terms of the health of the system. Yeah, shard management, as I mentioned, like clear scenarios for when something goes down, when you need to spin up a new replica, and yeah, every process is covered. And yeah, there are exceptions to everything, like it usually is. That's everything. Any questions?
You said that in these, if you are using Facebook app, then I have one connection to one application server. But if I'm using a browser, then it's also going to the same application server, or how to exploit this local cache then?
It's local, not on the machine. It's local on the application server.
Yeah, but if I'm browsing through browser,
Yeah.
it's going to the same application server?
I think if it's different device, it will probably stick to a different one, so you're not going to utilize the same L1 cache. It's like maybe per session. Yeah?
Hi, yeah. So, you stated that there are a lot of advantages of using Tao, but for me it looks like it introduces also a lot of limitations, especially when we're speaking about some kind of complex queries. Is it?
Do you have an example?
In your example, it was mentioned that there are several simple methods like adds, delete, something like that. But if we need some complex joins or something like that, that valuable abstraction can also limit.
In some way, but I think in this scenario, it's better to have that limitation rather than give you, because like again, dealing with joins is, first of all, you want to avoid join as much as possible. But even if there is a join, it's better for a database team to deal with optimizing and tuning it rather than for the like application developers.
So are there any disadvantages of using Tao?
I mean, I think at that scale, it's necessary, because like you can no longer deal with that complexity of like what happens under the hood. Yeah, maybe in some cases. So I think it's probably when you need to customize something, you have a communication overhead. Like you need to speak to the database team to let them know that, oh, like I need this optimization or something. There's this an issue exists, and they will deal with it. So more like that overhead that you cannot just like go and fix it, you know, and index the right thing, create the right column, and like there you go. So like you create the communication overhead, but for the good.
About licenses, I wanted to ask how big part of all these technologies like RocksDB are open source, and are some other companies using these tools?
Well, RocksDB for sure. MyRocks, I'm not sure. I don't know. I think they open sourced it as well. But yeah, I can check. But I think it's open source. Yeah, in the back.
When you explained the evolution phase, you said that there was an insane amount of tooling around MySQL, so that was useful. So basically, you use MySQL as an API to access different storage engines, right? But since the storage engine changed quite drastically, did you have to also change the supporting tools as well? Because, well, there's no way you cannot take into account this nuance, or was it abstract enough just not to change anything, and since the engine changed, everything else just works?
Oh yeah, for sure. Even the whole engine itself was like fine-tuned and developed for their specific case. And the tooling, for sure. Like, I think what they inherited from MySQL just evolved naturally, like the replication stuff. But definitely some database tooling probably had to change as part of this migration. And like, by all means, it took like, more than a year to move from one to another.
So you still say that using the MySQL as API still paid off, like rather than switch the database engine directly?
Yeah, I think so. Yeah. From what I know, there's like, they considered different options, and that the approach taken was the most rational from their perspective.
How widely it's used in Facebook itself? Because like there's different products, different teams working on it. So like pages, I don't know, groups and etc. Marketplace, which appeared later, and Messenger, which is completely different by the nature, which is more of event-based. Is it used like everywhere, or there's different stacks and bundles that exist as well for storage?
Yeah, there's a mix of stacks. That's why I made that remark that it's particularly about the UDB, which is the database behind the Facebook app as we know it. The rest of the especially where it's acquisition, you acquire something with a different stack, and like an Instagram or WhatsApp, and you deal with that. And from like what I know from the public information as well, it's like right now you have the apps that run on ZPDB, apps that run on the MyRocks, and maybe even still some of the like more of a legacy like InnoDB type of tables as well. Like, I don't know, but it's probably the case.
But they could be split like in completely different environments, like same like pages. Is it the same product, or is it like a separate product? Because I know teams are for sure separated. Like, I mean, from product perspective, that's logical because you hit different targets. But I mean, technically, from what you know, like same pages have relation to users, right?
Yeah, like pages, you mean your page management stuff.
Well, there's like, for example, DevClub page there.
Yeah.
So like business page probably.
Yeah, that is part of the same app. Again, based on my knowledge from the way back then. But there are separate apps, of course, as well.
Maybe shorter question. You said like, we already discussed this briefly, but there's a lot of internal tooling in Facebook. When you get inside, so basically, and you at the moment you were already had a strong background. So how long it takes you to actually dive into all of this kitchen with like knife, which is not called knife anymore, and stuff like that?
Yeah, a while. Like you learn, and then you also like people who spend a lot of time there. You like unlearn because you live in like, oh, like what? How the hell do I do this? Like I need to find a sort of an open source of the real world example of the tool that does what the internal tool did to me. So like I think you spend first 3 months to understand, to like onboard in your team and understand what sort of tools like are used generally in your team, but then like you learn for the whole year like new stuff because there's like, nuances everywhere.
Is there internal academy of like internal tooling?
There's a very good like bootcamp and onboarding, and also when I was there, everything was like running on the internal like workplace product. So you had like an internal version of Facebook with like groups and everything. So you like you follow 100 groups and like you learn a ton of stuff from them, and documentation and everything. So it's pretty robust.
So no more questions for you.
Well,
oh, you also need to keep
This
track
year,
of if
this
you
year.
ask the question, make sure that you pick something from the.
So you want to take all dolphins there home?
I want to take Max and talk about Facebook for a while.
Okay. Any other questions? No? Chocolate time.
All right.
Yay!
Thank you.